Thank you very much for having me. Thank you very much for coming. So yeah, I like to think about those guys. So this is a DNA knot. So DNA likes to knot itself like your shoelaces do. And there's a mathematical study of those, and that's what I'm trying to explain. So if you think about molecules, like bigger molecules, not the simple ones you see in a beginner's class on chemistry, like DNA, it really matters how they sit in space and not so much what the building blocks are. And the geometric structures you see are very often those little knot pictures. So I don't have a nice story about my my past, but I have a picture of my life. So here's a picture of my life. So I'm from prehistorical times where everything was just, nowadays everything is wireless, it's great, it's absolutely great, but in prehistorical times there were those pictures always, and the kind of the fun fact is you can always undo them. You need a lot of patience obviously, but you can always undo those little knots. And kind of the idea I have in mind is that, well, this is a picture of my life and maybe of life in general, who knows, and there should be a mathematical study of those, and it's called knot theory, and it's fairly recent. So what we have seen here is a study of planets, Kepler and Newton, which is something like 500 years ago. In comparison, knot theory is roughly 80 to 100 years old, and so it took a really long time until people studied this mathematically, and most questions are really widely open, and you will see in a second why, because it's actually really fascinatingly complicated in some sense. And it's also not just useful for DNA, but you can also think about a cryptography problem, right? So cryptography likes something that is really hard to undo, so those pictures fit very well to cryptography. It's really an applicable field, it's absolutely great, and well, I'm certainly a pure mathematician, so it's also a beautiful field in sense of mathematics, where geometry and algebra, which look very different from the outset, but they go along very well in the setup of knot theory. So I'm trying to explain a little bit how to formulate my life in terms of knots. But you should really think in, well, there are a lot of applications. Again, here are some knotting of DNA on the right hand side. They even have names, so there's a whole tables of them. So this is called a granny, for example. As you can see, it looks like a granny, obviously. But the kind of knot theory models a lot of things, like shoelaces. We'll show you shoelaces in a second, and many other properties. Like in cryptography, you could think of systems as being knotted, and undoing it would be undoing your security for your emails, for example. So it's really beautiful as a field of mathematics. There's one difference to the shoelace picture, which I'm going to show you in a little animation. Let me start the animation. Oops, it's on the wrong screen. Here we go. So in mathematics, we like to tie the ends together. So your shoelaces obviously have not tied ends, and you can see here why, because if you don't do this, you can actually undo everything. Right? So if the ends are not tied together, I can just undo everything. And that's, by the way, how you really untie your shoelaces. So in mathematics, we like to think of those ends to be just glued together. So we get a closed string sitting in three space. And yeah, so this is an example of a knot. And this is exactly what the DNA does as well. So the DNA is really not, it's a shoelace picture is slightly different from the DNA picture. So let me stop the video. Okay, so that's what we do in knot theory. So you really just take a piece of string, you put it in three space, and it gets knotted in, well, kind of fancy ways. Really beautiful idea, goes back about 100 years. So here's another picture. So what you can do, if you really want to do this in practice, and I should have done that, of course, would be much better for a live demonstration. You just take a rope and you glue it together at one point by using some kind of adhesive tape or something, and you really can't undo it anymore. So this one is really knotted. It goes under, over, under, over, goes all the way around. It is called a trefoil knot, probably because it looks like a trefoil. And if you suddenly change it, like this one goes over, and now it goes under, then you can actually undo it. Maybe you could see it here, this strand goes over everything, so you can just pull it down here, and whatever you get is just a circle, which just really just looks like this picture here. So this is just a circle. If you undo it, and it's called the unknot because it's a circle. It's not knotted. And here's another video that we can really undo everything if you don't tie ends together. So this is a certain type of knot which is called the Taurus knot, and you can just really undo it if I don't close the ends. So let's run it again. So it gets very knotted, it wants to get very knotted, but if I don't close the ends, it just undoes itself by just redoing everything. Okay, so in knot theory, we just like those pictures, and we like to think of kind of how to classify those. Can you write down a list of a table of those knots which are different, and they're the same if you can deform them, if you can build them out of rope and deform them really in the real world in 3 space. Like this doesn't really look like a circle, but of course you can just pull it down and it will just be a circle. Okay, come on. And the way we do this, so on the right hand side is a beautiful picture of a knotted DNA again, and the people in chemistry really do the same as we do in mathematics. So what we do is, because it's a 3-dimensional object, 3 space is way too complicated for me. We have heard something about 7-dimensional spheres. This is just 3 space, it's already way too complicated. So what we do is we project it on the plane. Have a nice video for you in a second, and we will just study those shadows that you see here on the wall. Here's a nice video. So here's this 3-dimensional object. It's a nicely knotted picture, and well, give it a second and we'll project it onto the plane. Yeah, so you certainly can't undo it, and you should really just think of, we take a shadow, there's some light source somewhere, and you project it onto the plane. And it's kind of the same information, it's just now 2-dimensional, which you can really nicely draw on a picture, on a whiteboard, for example. So I try to draw a knot in a second, but I usually fail, so we'll see what happens. And the only extra information you need to take care of is which strand goes over and under, and then what you see is called a knot diagram. Okay, so the knot is a 3-dimensional object, and the knot diagram is the shadow that you project onto the wall. So let me try to draw a knot diagram. Well, we'll see what happens. Usually it always comes out to be trivial, you'll see. So fun fact, if you randomly draw a knot diagram, like you put a crossing somewhere and put more and more crossings, it's very likely that you will just draw the unknot. So let me try not to draw the unknot. Well, it looks a bit knotted to me. And the question you would like to ask then, okay, this certainly is knotted. That's exactly the same picture I showed you before, which is now not working. So this picture here, or on the previous slide, it was this picture here. Maybe I swapped over and under crossings, but otherwise it's the same picture. But you somehow still need to convince yourself whether this actually is knotted or not. And if you just look at it, it's obviously knotted. I mean, there's no way that this is the unknot, but how to mathematically prove it is a different question. And to convince you that this is not trivial, I have here a very, very nasty shadow for you of still the unknot. So the point is, when you project, it can be really, really crazy. It can get as nasty as you want. So on the right hand side, which I'm not trying to draw on the whiteboard, no way, that's actually the unknot, okay? So I don't know how you feel. My brain says it is not the unknot, obviously not. I mean, come on, this is knotted. But it actually is. And the problem in knot theory that we somehow need to find an answer to is that, well, we study those pictures, but how on earth can we tell what they really are, right? So this one is really nasty, and it's just a really, really ugly projection of a circle. And there's no easy way to tell whether it is a circle or not. A priori, There's no easy way. And people were struggling for many, many years trying to, well, not just undo this knot, but prove, for example, that this easy picture, which was just built out of rope on my previous slides, is trivial or not trivial. It's really a non-trivial question how you should actually attack this very, very real-world problem, like knotting your shoelaces. And this is where algebra enters, and this is where the story becomes really beautiful from my point of view. So let me show you roughly how we would do it. It's kind of okay, let's take it as a black box. I'm not really going to show you how this works. I can easily tell you later. It's really a simple, beautiful idea, which goes back to Jones. We'll see a picture of Jones in a second. And it's this idea that to any shadow, you associate something that is very easier to understand, an algebraic object. It might be a number, and for me, numbers are really simple. It's just an integer or a polynomial, some algebraic object of that form. And then you can just check. You just look at the object, and it's not, they're different, so they're different. So here, this is a left-handed version of the trefoil, and this is a right-handed version. Subtle difference, so here's a little bit bigger. So this goes over, under, over, and this goes under, over, under. And it's really hard. So people were thinking about, for 100 years, were thinking about how to prove that they're not the same. By not building, if you build them out of rope, you can convince yourself easily, but by mathematically proving that they're not the same. And it's really not clear how to do it. And then Jones comes around and tells us, okay, I associate a certain polynomial, and for historical reasons, my polynomial has a variable q. Just think of it x, it's just, historically it's q. Here's a polynomial, here's another polynomial. The polynomials are different, so the knots are different. Which is a really amazing argument, because then you can just tell all those things apart, in principle. You just associate a number or polynomial to each side and convince yourself that they're different or equal or whatever. It's a really great idea, right? So from just an algebraic object that you associate in a certain way, oops, the other way around, to a topological or a geometric object. And this is just really, really great. And this is where a very new field of mathematics enters and was born. It is called quantum algebra, which is basically a mixture between knot theory in one version and algebra in the other version. Because what really happens now, and this is really great, so here's a few more knots for you, a few more polynomials. A priori, there's no way you can tell whether they're different. Obviously, just staring at them, they are different, but you want a mathematical proof. And the way you do it is you look at the associated polynomials. Well, this is what they are, and they're all different. So all of these are different knots, and it's just really, really good. So you turn a geometric problem into an algebraic problem by just looking at something very simple, a number, a polynomial, whatever you like. And you have a mathematically clean proof instead of building out of rope.
Sorry. In the 3-1 knot, why is the q squared missing?
A q squared is missing? That could be just a typo. No, it's the same. Q to the fourth, q plus q.
So why is there no q squared term?
Yeah.
Why is there q squared missing?
I don't know, I'm asking.
No, it's not missing, she said. Why is it not there?
Yeah, why isn't it
not
there?
Okay. I haven't showed you how to calculate the polynomial, but
right.
You do a calculation and you get this answer.
Is there this might be silly, but is there a measure of knottiness, if that makes
A measure of knottiness. You can think of the polynomial itself as a measure of knottiness if you want. So they tend to get really complicated for huge knots. But it's just obviously just a rough measure. And I mean, the whole point for me is, this is great. You can mathematically prove that all of them are not the same, and just a small list, you can do this up to how many crossings. And kind of the fun fact, I'm not going too much into details, is that all algebraic operations, on polynomials, on numbers, are reflected on knots and vice versa. So you have algebraic, geometric operations on knots, and they are reflected in algebra, and you have algebraic operations that are reflected in knot theory. So in some sense, those fields are exactly the same. So here's an example. you could take two knots and you just glue them together. Here, let me just do this here. So you just change this little picture to this little picture, and you get a new knot. It's called hash. The operation is called hash, whatever. So j hash k. And it turns out if j has a certain polynomial and k has a certain polynomial, well, what can we do with polynomials? We can multiply polynomials, and this operation is a multiplication on knots, and the polynomial you get is a multiplication of the polynomials. There's something similar for addition and other properties, for polynomials. So really the key part here of the story is that algebra and geometry really reflect one another. They're kind of the same in the sense of quantum algebra, which is extremely amazing. A priori, there's no way why this guy should know some polynomial multiplication, right? But it does, which is really, really amazing. And to wrap up, I'll show you one more video, but to wrap up, so in the 1980s, that's very recent for mathematics, right? Like Kepler 500 years ago, or Newton, and this was 1980s. And then the Fields Medal was awarded to von Jones for basically discovering the story I just told you a little bit later. And the point here really is that algebra and geometry are kind of the same under this identification of quantum algebra. And then you can think of more fancy ways of studying those, and you get really cool new ideas into algebra by using geometry. So let me run the final video for you. So what I'm doing now, or what this video is doing, is actually knotting a sphere, so a ball, in 4 space. So it's a 3-dimensional video of 4 space, so we'll see what happens. So this is just a long hollow sphere. That's just a sphere, just a little ball. It's hollow, okay, it's hollow inside. And now it knots in 4 space. And the way this illustrates 4 space is the 4th dimension is the color. Okay, 4th dimension is the color. And now this thing knots itself. And it looks like it intersects, but it doesn't. Because green, blue, and red are far apart in the 4th dimension. So in 4 space, it actually doesn't intersect at all. It goes all the way here. Goes all the way in here. Again, same, it doesn't intersect because it's very far away. But on the other end, because blue needs to go through red via green, this is knotted. You can't pull it apart anymore. It's not intersecting itself, but it's knotted in 4 space. Well, it will cut the picture open in a second to convince yourself that this really works. Right, I said again, it's not knotted because I'm using the color here to distinguish it. And if you just look at the inside, sorry, it's not intersecting. If you look at the inside, because green is inside, you can't pull it out. Right? So from red to blue, you need to go through green. Okay, so that's those pictures of knot theory in higher dimensions, and what you get from it, very new, is new forms of algebra. Right? So higher dimensional polynomials and all that fun stuff. And it's again really related to all of these nice pictures. All right, that was my story. Thanks.